Okay, so last time we stopped, we essentially re-expressed the wave equations in a compact way, but not just in a compact way, in a more meaningful way with respect to the non-covariant formalism, in the sense that we joined both the wave equation, the inhomogeneous wave equation on the vector potential, along with the scalar potential in a unique Lorentz invariant formulation, in which we see that we have just one single object, one single mathematical object, which is the four-vector potential, which includes both the vector potential itself and the scalar potential. So the advantage is not just that it is a more compact way of including both equations, but it also that it is Lorentz invariant. So that's this is probably the most important aspect of this. And also the Lorentz gauge, you see that it's just a four divergence. So again, you appreciate the fact that Lorentz gauge is also Lorentz invariant, because this is a four divergence of a four vector. So when it is zero in one reference frame, it is automatically zero in all reference frames. Okay, so let's see now how can we express, because in the end we are interested in deriving in both electromagnetic fields, not just so the four potential vector is just the four vector potential is just a means to get to the goal of estimating both E and B. So in the light of this new formulation, let's see what both the electric field and the magnetic field what they look like, essentially. So let's start with the electric field. So now let's take the X component, for example. The X component, okay, this is just this guy here. Now you see there is a mixture of the X component of the vector potential and phi. Now look at here, in particular the covariant coordinates of the four vector potentials. So essentially phi is the zero component, and minus ax, minus ay, minus az are the three spatial components for the covariant. If I instead consider the contravariant, of course, there is no minus sign, okay? So now, if you look at this, you see the time derivative, 1 over c time derivative of ax. Well, the time derivative is just delta, is just a partial derivative with respect to 0, okay? And a1, if you pay attention, a1 with 1 as a subscript is just minus ax. Look at here, it comes from here. So the minus you can attach to ax. So 1c over 1c partial derivative with respect to time of minus ax is just d0 a1, just like that. Instead, when you partially derive with respect to x, it's exactly like deriving with respect to 1. X here is the contravariant component of the space-time vector, for vector. And instead, a0 is just phi. So this guy here is simply minus partial with respect to 1, partial with respect to 1 of a0. If you work out the very same, I didn't do it here, but you can do it straight away. If you carry out the same exercise on y and z components, you see that in the case of EY, you have delta 0 A2 minus delta 2 A0. Easy, because the only thing that changes is y instead of x, so 2 instead of 1. The rest is just the same. So immediately see that this holds very similar formula holds also for the other two components of the electric field. Let's have a look at B instead. Well, again, let's take just the x component. The x component is just, well, it's just this guy here. The curl of A, take the x component, you just have the mixture of the other two components of the field and the partial derivatives. Now, again, look at the covariant coordinates of the four-vector potential. You see, you have minus AY. Minus AY is A2. And partial derivative with respect to Z is just delta 3. So delta 3, A2, I call delta, but that should be partial derivative, but it's just a short way to say. And then, again, Z, you have plus AZ. But let's consider plus as minus minus. So minus AZ is A3. So minus partial derivative with respect to y, which is delta 2 minus delta 2 A3. Very simple. So Bx, so the x component, which we associate with 1, index 1, is this guy here. It's possible to summarize into a unique object the three components of both the electric field and the magnetic fields into one single object, which is this guy here, which is a rank 2 tensor, which we call F mu nu, which by definition is defined as the partial derivative of A nu with respect to x mu minus you swap the two indices. So again, here is the same way. So from what we've seen in the previous slide, you see that you would expect at some point that some of the coordinates, some of the values of this new two-rank tensor are just the components of either the electric field or the magnetic field. We've just seen a couple of examples, but you can, as I said, you can check it out for all of the 6 components. This notation is also another equivalent notation. When you see in relativity, comma either as a subscript, as in this case, or as a superscript, comma something, comma index means partial derivative with respect to that index. Okay, it's just a very compact way of writing the same thing. So you see, partial derivative with respect to mu means that this guy here gains an extra factor of an extra index of comma mu. This is indeed a tensor. Why? Because it is defined by definition. When you start with a 4-vector a mu, whatever you want, and you partially derive, you know that this guy behaves like, this operator behaves like adding an extra index. So moving, it transforms a 4-vector in this case to rank 2 tensor. So it is a tensor. So what does this mean? What's the implication of this? Well, it implies that when you move from one reference frame to the other one, it transforms according to the way we've just seen. So this is an important point. Second property, which is apparent from the definition itself, is that it is an antisymmetric. If you swap mu and nu, of course, you get minus the same guy. So this is very important because it means that all the diagonal terms are 0. Whenever the two indices are equal, of course, it means that this guy is 0. This is called electromagnetic tensor because we will see now full, but we've just had a starter that indeed the coefficients of this tensor are indeed the components of both electric and magnetic fields. So that's the reason of the name, but also field strength tensor, because essentially it gives you the intensity, not the intensity, the strength of both fields, of both electromagnetic fields. So you might find in the literature the same names. Here on the right, I just again put what we know, specifically the space-time 4-vector, which describe events. and in both contravariant and covariant coordinates, as well as the same for the four-vector potential, because we see that by definition the electromagnetic tensor is defined as a function of the four-vector potential. It's interesting to see that definition of both, well, of the both electromagnetic field as a function of the four potential. Of course, here, but the definition I gave you for the electromagnetic tensor is using the coordinates in the covariant coordinates. So the resulting guy is just from this definition expressed as a covariant tensor. Of course, as for any other rank 2 covariant tensor, you can switch to its contravariant version just by contracting with a metric tensor. Since this is a rank 2 tensor, you have to contract twice. So you see, you kind of raise, to speak with an equivalent way of saying, you raise each individual index. So you have two indices from alpha and beta, you have to raise both. So to raise alpha, you contract with eta mu alpha, and you raise alpha. And then if you want to raise the beta index, you have to also contract with another metric tensor, beta nu. So if you also, I remind you, we are in the flat space-time, so the metric tensor is just the Minkowski one. So very easy, and if you remember the rules, when you raise and lower indices, you immediately see the rules. So essentially, you can also define the contravariant equivalent contravariant coordinates of the electromagnetic tensor just by raising all the index that you have here. It's just the same. Remember, it would be good for anyone to remember this, because it's not a big deal to remember this guy, and it's important to remember that the first index relates to the derivative, and then the second one is just, and then minus the opposite one. Yes, this is what it looks like. This is the covariant coordinate. These are the covariant coordinates of the electromagnetic tensor. So you immediately see, and you can see just from, you see, that's the reason why I reminded you here. I put both the electric and magnetic field as a function of the corresponding potentials, and here the potentials, because you can immediately check one by one that indeed all the coefficients of this guy are indeed what you get out of this. We just saw before, in the previous slide, we just saw a couple of examples, the x-coordinate for both electric and magnetic field. What is immediately to be noticed is the fact that if you look at that, and in here I also put the contravariant coordinates of the same guy. If you notice, the electric field components are just in the mixed places. So mixed means that one of the two indices is 0. Okay, so in this case, 0 the column, or 0 the row, or 0 the column. So first of all, you see that, as I said, this is completely antisymmetric tensor. And then you see, in the mixed coordinates, in the mixed components, you have the electric field, while the components of the magnetic field lie in the spatial indices, in the spatial places. So this is 1, 2, this is 1, 3, and this is 2, 3. Okay, this is something which is worth noting. And if you compare both the covariant and the contravariant, you see that applying the rule, when you raise 0, the sign doesn't change. When you raise 1, 2, 3, the sign changes. Here you raise twice. You raise two indices. So you see, when you raise, well, 0, 0, of course, is the same. In particular, here is 0, so it doesn't make any difference anyway. But if you look at the spatial index, you raise 2. So you change sign twice, which is equivalent to no change of sign. In fact, the spatial part is exactly the same, you see. The only part that changes sign is the mixed one. 1, 2, 0, 1, 0, 2, 0, 3, and also the column. And this is obvious if you think, because you raise two indices, one of which is temporal and the other one is spatial. So you change sign just once. So easy to, there's no, it's not worth to just remember both of them. You remember one and then you can immediately get the other one. Or if you remember the definition, then you have to remember. I mean, it's useful to make sure. When I was a student, I just wanted to make sure that I could, just by remembering a few things, for example, the definition itself of the electromagnetic tensor, you may make sure that you can just derive all the 6 coefficients. So the entire electromagnetic tensor coefficients in both, of course, contravariant and covariant coordinates. Having defined the electromagnetic tensor, so you see the electromagnetic tensor is something which is a tensor, so it behaves correspondingly, and it encodes both fields. It has 6 independent components, which are the components of the both fields. Having defined, as I said, the electromagnetic tensor, you can also define the so-called dual electromagnetic tensor. And by definition, again, and I call the dual as F tilde mu nu, which by definition, you see, is the contraction of the electromagnetic tensor itself, and this guy here, which, if you remember, is the Levi-Civita tensor, is a 4-rank tensor. So you get, again, you see, you have a rank 4 tensor contracted with a rank 2 tensor. So the result is a rank 2 tensor. And indeed, I'm still implicitly assuming the Einstein summation convention. So rho and sigma in the specific case are mute indices, are summed. So you are just left with mu and nu. So again, these are 2 tensors. So as a consequence, by the newly defined dual tensor is also a tensor. So you see the power of just dealing with objects, 4 vectors, rank 2, 3, 4 tensor, whatever. The advantage of that is that whenever you find relations, equations, which connect tensors, quantities, it means that it is automatically Lorentz invariant. If it is true in one reference frame, it is automatically true in every other reference frame. So why is this important? Also the dual tensor. Well, first of all, let's have a look at what it looks like. For example, if you consider nu as 0, well, nu as 0, it means that Fi is just, you take the ith row and you take the 0th column. So here, well, this is F, this is the contravariant, pay attention. Yes, I didn't. Yes, essentially, the point here is that it is found that you have a swap between the electric components and the magnetic component. How to see that? Well, it's just followed by from the definition. But essentially, you see that the mixed components are taken now instead of by the electric field, as in this case, this is the electromagnetic tensor, are the magnetic component. Instead, the spatial ones are just, in this case, connected with the electric field. So there's a swap between the two fields, essentially. And this is what it looks like, you see. By definition, well, you can have fun and see why this is the case for every single, because the Levi-Civita tensor, essentially, if you remember, it's 0 whenever any 2 indices are equal. So, for example, if you have I0 as mu and nu, it means that the only things that are left is when these 2 guys are 2 and 3. So when picking up I0, you have to go to 2, 3. 2, 3 means here. consider here. Okay, anyway, you can check it out. That indeed there is this swap here between the two. Yes, I was looking here, but I should have looked here. So if again, just to prove this guy here, when rho and sigma are 2, 3, 2, 3 means that you get here. So minus bx, which is indeed, for example, if I is 1. So indeed, you see, if you compare the two, what I said for the electric field in the case of the for the electromagnetic tensor, for the dual there is the opposite way. So the magnetic field lies in the shows up in the mixed components, while in the spatial ones you have the electric field. But the important point is that it is also a tensor. So, and the usefulness, some of the useful implications of this is that in particular, I want to focus on two of them. If you contract, just consider the electromagnetic tensor. If you contract the electromagnetic tensor with itself on both indices, so you are contracting a rank 2 tensor on a rank 2 tensor, so it means that the result is a rank 0 tensor. Rank 0 tensor is just a scalar which is Lorentz invariant, because it is a 4 scalar. So if you contract this guy here, which means that you have to multiply each single component by itself, and then you sum up, you see that doing this exercise here, for example, well, taking into account that you have to change sign for the mixed component, it is immediate to see that the resulting scalar is just -2 times the difference of the moduli squared of the two fields. But you see, this is important. Why? Because this guy, which is a scalar, is Lorentz invariant. So it means that whenever the two fields have the same magnitude, whenever means if there is a reference frame in which the two fields have the same magnitude, that holds true for any other inertial reference frame, because this quantity is Lorentz invariant. So it means that we already saw a special case in which both electric and magnetic fields have the same magnitude, which is a plane wave, if you remember. So it means that if you describe a given plane wave in one reference frame, and you find, of course, you know that already that the two fields have the same magnitude, that means that this property will hold for any other reference frame. So it's a Lorentz invariant property. Very important. The second one is that if you contract now the electromagnetic field with its dual mate, it means that again you are contracted to tensor. So again, what you come up with is a Lorentz invariant scalar. But again, if you multiply the corresponding components, you see from this guy here and the other guy here, well, here, not exactly this one, you have to consider the covariant way, but you immediately see that you are mixing, you get a number of mixed scalar products between the two fields. And indeed, it's straightforward to check that the result is -4 scalar product between the two fields. Again, this is Lorentz invariant. So it means in particular when this product is 0, which means that the two fields are perpendicular, orthogonal, it means that this holds true in every other inertial reference frame. So again, when they are perpendicular to one another in one reference frame, it means that they are in every other inertial reference frame. So you see the very, very important, very powerful implications just following from the definition, from the properties of just being tensors. So this is really, really important. But you see, the overall, one of the most important consequences of this, you can immediately appreciate it, which means it's telling you, well, look, relativity, special relativity is telling us that the two fields magnetic field and electric fields are not two separate entities. They do not behave and change and transform when moving from one reference frame to the another one in an independent way as two different distinct entities. No, they are the same. They belong to the same object, to the same entity, to the same geometric object. And this object doesn't behave, doesn't transform, is not a full vector, but it is a rank 2 tensor. So they are part of the same creature, let me say, of the same object. This is a breakthrough if you compare it with the way that in classical physics, non-relativistic, the two fields are treated. So this is a powerful result. In particular, it's very interesting to explore how they transform now, considering specific cases. So let's consider again our system, two reference frames, one which we consider as fixed, and the other one which is moving with constant velocity. Again, for simplicity, we consider a boost along the x-axis. So we start with the electromagnetic tensor in the fixed frame, so this guy here. We want to know what it looks like in the prime system. So our goal now is to find the electric and magnetic field components in the primed, in the moving system with respect to the unprimed quantities. So in a word, we want to see how the both fields transform. What are you expected to do? Well, you know that. This is, for example, here I wrote its contravariant components. So you just have to apply twice the Lorentz transformation. So you have to just for each indexes. So the rules that we already saw. In particular, you can apply just the rules of matrix multiplications, just making sure that, of course, you follow the right order. So, for example, here, you can exploit the fact that, for example, the Lorentz transformation matrix is just a symmetric one, so you can swap the two indices. So, for example, you do this times this. You make sure that you combine, of course, the column index with the corresponding row index, and then you have two matrix multiplications. I invite you to make sure to verify that the result is this one. In particular, of course, the result is f prime will be something like this with all prime quantities instead of, and then this guy has to be equal to the result of this double matrix multiplication. If you do that, you will see that you end up with this guy here. This is particularly, I'm not gonna do it just every single, because it takes a while. You've got to battle away at some algebra, as I said, but it's just a matter of multiplying matrices. So it's a useful exercise to carry out at least once in your lifetime. So I invite you to do that. Also to make sure that you are in control of things. And it's interesting to see that immediately and somehow expectedly, I would say, you see that there is kind of mixture, or in particular, or to be more precise, you see that the components of the fields which are parallel to the direction of motion, we chose in this case x. So you see that the x component of both the electric field and the magnetic field are left unchanged. But this is no more the case for the perpendicular ones. In particular, you see that EY prime and EY and EZ prime, as well as the corresponding component for the magnetic field, not only there's a factor of gamma, but there are two aspects which are important. There's a factor of gamma, so it means that when you are considering relativistic reference frames, relativistic, I mean when gamma can be much larger than 1, this makes a huge difference with respect to what you would expect from non-relativistic treatment. But also, the two fields get mixed. In particular, we can compact this result by just joining. I just wrote in terms of parallel and perpendicular. So you see that both parallel components of both fields are left unaffected, do not change, while the perpendicular one can be summarized as, you see this guy here. Okay, the corresponding perpendicular times gamma, but the new point which encodes the mixture of both fields can be expressed as a vector product. And here beta is the velocity of the moving system with respect to the fixed one in unit of speed of light, of course. So in this case, beta is as just the only component of beta is along x. Okay, so it would be just beta x. And you immediately see, for example, if you take e prime y, you see that here, concerning the beta component, is just the bz, because you have just b. The only component of beta which is non-zero is bx, beta x. So to have a y component, the only way is just to have here. This is very, very interesting, because you can have fun in considering all the many important aspects. For example, there was one thing which really before Einstein could accomplish the formulation of special relativity. What motivated Einstein towards what he finally obtained with special relativity? What really annoyed him was the fact that the total asymmetric description of the same electromagnetic phenomenon as seen in two different reference frames. For example, he just said this in its seminal paper of 1905, which essentially is the paper which lay the foundation of special relativity. And the title of that paper, that incredible paper, one of the most important papers ever written in the history of physics, the title was in German, was Elektrodynamik bewegter Körper, which means electrodynamics of moving bodies. And he says, if you think you have a magnet and you have a circuit, a conducting wire, closed wire, a circuit, if you move one with respect to the other, for example, if you keep the circuit stationary and you move the magnet, your description is that you have the charges within the electrons within the circuit feels a time-varying magnetic field. So as a result, there is Faraday's induction. Okay, so they feel at some point an electromotive force, which is the reason of the Hall effect, if you want. While, he says, the very same phenomenon, so in this case, you see, you have essentially, you have the creation of an electric field within the circuit because of Faraday's induction, he says. So in this case, he says, there is an electric field which shows up. If you describe the same phenomenon in the co-moving frame of the electromagnetic, of the magnet, so you keep the magnet still and the circuit is moving, here you don't see any, you don't call for any electric field. You say, how do you describe this? You describe, oh, you have a magnetic field, you have charges moving within a magnetic field, so they feel the Lorentz force, so charges are displaced, so there is a potential difference which is created. So you have a completely different description, he says. Of course, the phenomenon is the same, but depending on whether you describe it from one in reference frame or in the other, you you physicists give a different description. In one case, you say, oh, there's an electric field. In the other case, there's no electric field. This fact really annoyed him. And now you can see this. You can look at the description of what happens, and you immediately see why relativity just provides a much more homogeneous description. Because even if in one reference frame you don't have any electric field, in the other frame you have electric field just due to the fact that there is a motion with respect to the magnetic field. If you think of the electromagnetic tensor, it's no more any wonder. There is no more this asymmetry, because both electric and magnetic field are part of the same object. So when you change reference frame, you are looking at the same object from a different point of view. So the coordinates of the object change, but the object itself doesn't. Which means, of course, if the coordinates of the object, and the object I mean, of course, the electromagnetic tensor, are both the electric and magnetic field, it's no wonder that in some reference frame you just see either electric field or just magnetic field, while in the other one you see both. So this is really, really interesting. So it is also interesting to see this in the light of this equation. So there is no more any qualitative different description. You are just looking at the same object in two different reference frames. So it's no wonder that, of course, the coordinates changes. The coordinates change much in the same way that you have a geometric object that, depending on the reference frame which you consider, the single individual coordinates change, but not the object itself. It's just a matter of different projections. Here, the guy that you are projecting is made of electric and magnetic field. So depending on the reference frame which you project, you end up with magnetic or electric field, or both, or dependent. But there's no more this huge difference in terms of description. So this is we can imagine how pleasing this was finally for Einstein, because this is really. So I want to stress here the role of electromagnetism, its historic role in just driving, in motivating Einstein. It's not just the constancy of speed of light. Well, we know that this is one of the basic principles of relativity, but it's not that which motivated him historically. It was this stuff here. So it's beautiful now to see this also in this historical perspective. Okay, here it's just, of course, both fields are just the sum of both components. A very special case. So you not only recover a more homogeneous description of electromagnetic phenomena thanks to this covariant formulation, but this formulation allows also to explore regimes which are not accessible with non-relativistic physics. In particular, for example, let's investigate what happens when we consider ultra-relativistic motions. So in particular, let's consider the electromagnetic field produced by a charged particle which is moving at relativistic speed. How can you do that? Easy. We consider the comoving frame of the particle. So in the comoving frame of the particle, here you see on the right, I just rewrote the very same transformations that we obtained in the previous slide, but I wrote here the inverse transformations. If you look at that, I express the unprimed quantities as a function of the primed quantities. And how can I do that? Well, the trick is always the same. Change sign of beta. You swap the unprimed indices with the prime indices at the price of just changing sign of beta, because moving from the prime system to the unprimed system is like making a Lorentz transformation with minus v, just like that. So if you compare the two, I just changed sign of beta, and of course swapped the prime and unprimed quantities. Why this? Because now the goal, why we are going to use this? Because we start from considering the electromagnetic field in the moving frame of the particle, and we want to derive the corresponding fields in the lap frame, let me call it. Why is this convenient? Well, because in the moving frame, the field produced by the charged particle is obvious. And it's obviously it is obvious because this is exactly what you have in panel A here on the top left. The particle is stationary in this frame. It's a charged particle, so you have the Coulomb field, just like that. So you don't have any magnetic field. You have just a single particle which is stationary. There's no magnetic field in the moving frame, of course. And the only thing that you have is the electric field, which just is the electric field that you would expect from a stationary charged particle. So it's radially and just depends on distance. Of course, this can be considered also for very small velocities as compared to, but let's consider just the moving frame. Now, let's consider in particular the extreme case of an ultra-relativistic particle. So when gamma is much larger than 1. So you see, just look at these transformations and you immediately see what happens. So again, the parallel, you have no beta B prime, there is no magnetic field in the moving frame. So B prime, parallel B prime, perpendicular are 0. And that's why here I neglected these terms. So there is no component of the parallel field. How does the electric field changes? Well, you have to pay attention because both components, parallel and perpendicular, behave in a different way. To appreciate this, you have to see that, look at panel C here. Panel C, it shows the electric field in the moving frame. So for a generic position here, let's suppose the particle is here, and you want to calculate the electric field there, where the arrow lies. So you have an EX component, EX prime, EY prime. And of course, since the electric field is radially directed, it means that it has the same direction as the position vector. Now, when you move from the moving frame to the lap frame, you see that the EX is just the same because the parallel component remains unaffected. But instead, if you look at the perpendicular component of the electric field, this guy here, you see that here I just dropped this term because because B prime is 0. There's no magnetic field in the moving frame. That's why this guy here becomes this here. And the same here. This guy here becomes, B prime is 0. So you see that the perpendicular component of the electric field is amplified by a factor of gamma. So when gamma is much larger than 1, it means that the Y component is much larger than this guy here. So the result is that the electric field is pointing more towards a perpendicular direction because you gain much more in a perpendicular direction with respect to the line of motion. So looking at panel B, that's the field lines of the electric field in the lap frame. You see that you gained in the perpendicular direction much more than you didn't gain anything in the parallel. You gained a lot of. So the result, these lines here in the moving frame, in the lap frame, look this way. So this is what the electric field lines look like. But now that you know this, you can also see how the magnetic field, and you see there is magnetic field. So you immediately see what I was commenting before. From just a purely electric field in the moving frame, you have magnetic field in the lap frame. And if you think of course, this was new also prior to special relativity, but it took people a more complex description of all the phenomena. You had to say, oh, you have to call for the Ampere's law or Biot-Savart law. Whenever you have moving charges create a magnetic field. So, for example, you use the Laplace formula to work out the magnetic field. But you see, you have to combine different laws. Here is just this guy, electromagnetic tensor. You just apply Lorentz transformation, and you immediately see it's just starting from a purely electric field and nothing more in one reference frame, the moving frame of the particle. You end up with a magnetic field in the. This is just where Biot-Savart, Ampere's law come from, in a very compact, unique, and much more elegant way. You see, and let's have a look what the magnetic field looks like in the lab frame. Well, you see, it's just here. Beta is pointing, of course, in the same direction as V, velocity of a particle, and E prime. E prime is the guy in panel A. So if you work out this product for all possible direction, you see that the resulting magnetic field is a kind of solenoidal line field. It is exactly what you would expect, what you already know in the case of, as I said, Biot-Savart law, for example. Think of a long wire, you know very well what the magnetic field is. So this is just this guy. But in addition, you have an extra result. You also see the effect of an ultra-relativistic motion, because it's not just beta vector E prime, but you also have a factor of gamma. So it means that when the particle is ultra-relativistic, the magnetic field is correspondingly stronger. And you immediately see here that B in, B out means that B is entering or coming out of the page. Make sure everything is according to what you see. So you see, this really enormous result, because not only does it provide us with a much more elegant, unified picture of electromagnetic phenomena, but also it allows us to explore the ultra-relativistic regime. In particular, we see that what is affected in the case of the fields is, in the case of one single particle, which is moving at relativistic speed, you see that the perpendicular component of the electric field gets really strongly enhanced by a factor of gamma, as well as the perpendicular component of the magnetic field, and there's no other component other than perpendicular. So a lot of things that are really worth noting. Of course, if the particle is accelerating, you already know what happens, and both in the non-relativistic, so in the comoving frame, instantly comoving frame, and in the lab frame, something we already talked about. So getting back to our friends, old friend, new and old friend event. So this is the electromagnetic tensor we defined. You can, you have a rank 2 tensor, so you can calculate its 4 divergence, which means, of course, the 4 divergence of a rank 2 tensor is a rank 1 tensor, because you contract one of the 2 indices. So you're left with just one, which means one tensor, one vector, 1,4 vector, or if you want, rank 1 tensor. And what is this guy? Well, let's have a look. You see, just by definition, you take the definition of this guy, and you see here that you can, of course, you can swap the derivatives. You see, you have the 4 divergence of the 4 vector field. But again, we are in the Lorentz gauge. So, and this is 0. So it means that the 4 divergence is just this guy here, just the first term. But again, if you see the operator delta mu, this is a guy we know very well. Well, this is the D'Alembert. And we already saw that this guy here, the wave equations, written in the covariant way. So you immediately see that instead of going through the full vector potential, you can express Maxwell equations just starting from the electromagnetic tensor. So in this case, four of the well, four in the scalar sense, but considering the four Maxwell equations, you immediately see that this equation just encodes just two of them. The ones which are related to the charge density, of course, and the current density, just because of the four current showing up here. So by using this guy here equal to this, you have two Maxwell equation in a covariant way, because you have a full vector, which is the result of a full divergence of a rank 2 tensor, equals a full vector, Lorentz invariant, the Lorentz covariant. So the very same equation doesn't change, varies along with. Both terms are in the specific case are full vectors, so they change accordingly. This is really incredible. And the other two Maxwell equations, I let you verify. Indeed, it is, well, the interesting case, having already known that the electromagnetic tensor is an antisymmetric tensor, this is telling you something informative only when the three indices are different. Okay, so you have mu, rho, and sigma. They can assume four possible different values. So it means that from this equation, if you consider all the possible combination of indices, it means that you have to choose 3 out of 4. So you have 4 possibilities when for each of one is you consider the only index that you left out of the choice. So if this guy is 1, 2, 3, this corresponds to ignoring index 0 and so on. So you end up with 4 equations, 4 scalar equations. But these 4 scalar equations are just these guys here. This is a vector equation. This is a scalar equation. I'm not gonna. Again, I let you know very well how to see that. Just consider 1, 2, 3, 1, 2, 3, 1, 2, 3, and just 1, 2, 3. You see, it means that you work out spatial derivatives of things that lies in here in the spatial part here. So it means there is a divergence of the magnetic field. While instead, when the indexes, which you don't consider is one of the spatial index, you get mixed. You get both the electric field. I mean, it's just a matter of making sure that indeed this is the case. So if you consider both, this one here and this one here, you buy all of the 4 Maxwell equations in terms of a covariant relations, as covariant relations. So this is a covariant formulations of Maxwell equation. Extremely powerful. Just using, the full vector, the full current, sorry, and from the knowledge of the full current, you automatically derive the goal of solving Maxwell equation now becomes finding the electromagnetic tensor. And indeed, once you know the electromagnetic tensor, is equivalent to knowing both electric and magnetic field. So the task here is equivalent, solving Maxwell equation is equivalent to determining the electromagnetic tensor. And all this is in a fully covariant way, which is extremely powerful and beautiful. Yes, so this summarizes what I just said. So the combination of these two equations just includes all of the 4 Maxwell equations, where, of course, this is a reminder of what the full current is a full vector with the charge density and the current density. And also, I remind you the charge conservation. which is the continuity equation, but written this way is, again, even more powerful, because you immediately see that this guy is a Lorentz invariant scalar. So if charge conservation is charge is conserved in one reference frame, is automatically conserved in all reference frame. And charge must be conserved, because if you end up having an electromagnetic tensor that satisfies these equations, automatically charge conservation can be proven just from following Maxwell equation. Is a consequence. So whenever you have a solution of Maxwell equation, it means that automatically, necessarily, the charge conservation is satisfied, so that for current, in this case, its divergence is 0. You can have fun. Here I just did it. What? To verify, indeed, that from these equations you get Maxwell equations. For example, the first one here, you see, if you consider the first one with nu equals 0, well, in that case, of course, given that this is the f is an antisymmetric tensor, so it means that mu goes from 1 to 3, so just I, Latin index. But again, if you have in mind f, I0 means that they are in the mixed component. The mixed component are just filled in by the electric field. This is the divergence of the electric field. But the divergence of the electric field is this guy here with J nu equals 0. Nu equals 0 is C rho, so 4 pi rho. The first one, or the Coulomb, the equivalent of the Coulomb's law, or just the Gauss theorem. And then for the spatial one, when mu instead of 0 is either 1, 2, or 3, you get the Faraday's law. Sorry, the Ampere's law, what I say. And then, of course, from the other one, as I said previously, I just put it here. Sorry, it takes a while to make sure that, depends on how quick you are in carrying out calculations. There's no point for me to go through every single passage. I just wanted to put all of them just to allow you to have something to compare with. But I don't want to comment. Once you understood the mechanisms, how it works, it's just a matter of it takes a few minutes, but I advise you to do that on your own at least once. Not only for the pleasure itself of verifying that this is indeed the case, but also is a test to make sure that you are in control of things. You are not confusing between covariant and contravariant components, and this is a good test. And also to get familiar with this object, which is very important. And yes, and so for the other two laws, so the null divergence of the magnetic field and Faraday's law. So let's summarize what we've come up with. So having given the definition of four current, so once you know charge densities and current densities, you can essentially you can choose between two possible ways. Either you set the task of obtaining the full vector potential, or you work directly on the electromagnetic tensor. So in one case, having to do with these two ones, what you are supposed to solve is just the wave equations. The wave equation in homogeneous case. You know J mu, you automatically solve the equation, you find the full vector potentials. Once you know the full vector potentials, of course you know how to derive both the electric field and magnetic field. Or in a fully equivalent way, you don't care about the full vector potentials, you just start from J mu and you solve Maxwell equations, but Maxwell equations expressed in a covariant way, which means you have to solve these equations. So you have to find the individual components, coordinates of the electromagnetic tensor, which means solving Maxwell equations in a covariant way. So either this way or this way, the result is equivalently, which means you derive the electromagnetic fields in a fully covariant way. And once you know them in one reference frame, you know how to transform to the other one, which is exactly what we did in one single example. The very last aspect that I would like to investigate with you is about electrodynamics, which means study the behavior of charged particles under the influence of electromagnetic fields. And let's see now in the new context of a covariant formulation. Let's see in what new light this shows up. So let's start with what we know. So a charge which is subject to the action of an electromagnetic field, of course, feels this force here. So with P, I denoted the momentum of the charge, Q, and of course, this is just the Lorentz force. So the Coulomb term plus the Lorentz force in the lab frame in which the particle has a given beta. Beta is its velocity over c. Now, of course, expressed in this way, this is everything but covariant. When you change the reference frame, everything changes here. But you see, oh, by the way, I didn't say that yet, but probably you noticed that when I was speaking about Lorentz gauge, I wrote Lorentz without T. Here speaking about Lorentz transformation, as you know, Lorentz is written with TZ. It's not just a typo. There are two different guys, so make sure you know. So Lorentz here is Hendrik Lorentz. He was a Dutch scientist. And the other Lorentz was another, I don't remember his name, but they are two different guys, so it's not typo. Okay, so the momentum, the linear momentum. Well, we know that the momentum is not an object living on its own. It's part of a four vector, which is the momentum energy four vector, whose contravariant component here is wrote as P mu. And just to remind ourselves, P mu can be thought of as a temporal component, which is energy, well, over c, if you want, of course, homogeneous quantity, and the real momentum. But this can be also expressed as mc times u, where u is the forward velocity, which I remind you we define as the forward velocity dx mu over something which must be Lorentz invariant, so the interval ds. ds is c d tau, where tau is the proper time. I remind you again that many textbooks define the forward velocity as dimensional point of view as a velocity. Here it's an adimensional point of view. So remember there is a factor of c which could be different. So don't be confused if you see that, oh, there's a factor of c, which, yes, it depends on how forward velocity is defined. Here I use the adimensional definition, so over c. So we already saw in the very first classes when we were dealing with special relativity in astrophysics that the forward velocity is nothing but gamma and gamma beta, where gamma is the temporal component and gamma beta is the spatial one. And let's denote this as capital U, as I wrote here, with U0, the temporal component, and vector U as the spatial one. So you immediately see that you can express also the full momentum energy, full vector, as a function of the full velocity, just like that. Let's make it more explicit. So the linear momentum in relativity of a particle, you know very well, is not the just mv, the Newtonian momentum, but it's the Newtonian momentum times the Lorentz factor, as well as the total energy of a particle with Lorentz factor gamma is gamma mc squared. But here, of course, I want to have homogeneous quantity, so this is just energy over c, which is exactly what I wrote here. Here, you may note that I use for the total energy of a particle this calligraphic E, not to be confused with capital E, which in this context is just the electric field, okay? So I just use the different notation just to avoid any confusion. So this is indeed the full energy of the particle. So let's consider again this guy. Instead of the goal is the final goal, what is that? Is to reach a covariant formulation of the dynamic of the charged particle. Now we want to move to something which is Lorentz invariant. Use the Lorentz invariant quantity. So in particular, instead of dt, I express dt as a function of the corresponding proper time interval. So if you remember, dt is gamma d tau. So if you replace with dt gamma d tau, and gamma here I put on the other side of the equation, you see you have just this one. Just like that. So I just replace dt with gamma d tau, just like that. And gamma goes on the other side of the equation. But now look, if you look at this, you immediately recognize that, look at the force velocity here. Gamma, you may see gamma as u0. So instead of gamma e, I wrote u0 e. And in particular, instead of gamma beta vector, if you see, this is just the spatial component of the force velocity. So it's vector u, just like that. You see the advantage? We are moving towards using objects which are four vectors for entities which live in the Minkowski space rather than. Now this concerns the momentum equation, so the equivalent, if you want, of the Newton's law applied to a particle, where of course you have to consider that the momentum is the momentum, the linear momentum in relativity, and all the things that we already said. Now let's consider energy. The time derivative of P0 is energy over c. So instead of P0, I just simply wrote energy over c. Instead of d tau, I considered again dt over gamma. D tau equals dt over gamma. So given that there's a denominator, over gamma means times gamma. Now, here we have the rate of change of energy of a given particle. But if you know the force acting on the particle, you know from the very first course of physics that many of you did with myself, that the power acting on a particle can be expressed as the force scalar the velocity of the particle. But you know, the force, what's the force here? Well, the force is the first equation we wrote above, with the exception that you can neglect the Lorentz term, because you are making a scalar product between the force and the velocity. So the second term just vanishes, because this is the famous term. The Lorentz force is always perpendicular to the force, so it makes no work. So the only term which contributes is E, QE. And in particular, so this guy here is just QE, the force, scalar, the velocity. So V scalar QE. But Q, of course, is a scalar. You can put it everywhere. Just like that. Now, if you look, you have gamma V over C, where V is vector. But gamma V over C is gamma beta vector. Gamma beta is U, is the spatial component of the force velocity. So you can immediately write this as Q U scalar E. Now, if you look at the two results that we've just come up with, so the rate of change of the linear momentum with respect to the proper time, and the rate of change of energy, except for a factor of 1 over c, with respect to the proper time, we expressed both quantities as a function of the electromagnetic field and the force velocity components. Now, I tell you, and I'll show you, that you can summarize both equations as in a unique way and in a covariant way, as operations between four vectors and tensors. In particular, I'll show you in a moment that indeed you can look at this as the contraction between the electromagnetic tensor and the full velocity, and what you come up with is just the rate of change of the full momentum with respect to proper time. So all fully covariant equation, you see? And if an equivalent way of expressing, if you exploit that the full momentum here, this one here, is also mc for velocity, you replace here, you see that you gain here a factor of mc, and then if you divide both sides for an extra c, you have c d tau is ds, the invariant quantity, the invariant interval, and here you have mc squared. It's interesting to see, you see, now we are going to prove this, but you see that you have the action of the electromagnetic field F mu nu over the velocity. And this is indeed the generalization in a covariant way of the Lorentz force and the kind of kinetic energy theorem, the way energy changes of a particle is the result of the action of a force. So electromagnetic fields acting on a given particle with a given force velocity gives you the rate of change. To see that, we'll see just right now. So let's start with the spatial component. So I just here copied the previous result we obtained. Here it's a reminder of the covariant component of the force velocity. So since these are covariant components, of course the spatial ones have minus sign. So let's have a look at the first. In particular, let's take the x component of this guy here. Well, the x component, px, ex, and of course this is a vector product, so the x component is just the mixture of y and z, okay? Now, I show you that we can write this as a function of the components of the electromagnetic field in a much more powerful way. How? Well, you already have u0, so you don't need to do anything. But ex, if you look at this guy here, ex is 1, 0, this guy here. Column 1, row 1, column 0. Now, this guy here, you have uy, but uy is minus u2. Minus u2, and here f12 is minus bz. So minus bz times minus y is f plus f1 u2. So this guy here is just this guy here. You see? And the third one, you have u3. u3 is minus uz. So minus uz. And then f13, column 1, row 1, column 3, by. Here it is. So indeed, you can write this as this way. But you see, this is the contraction of the second index with the first index fixed to 1. Very beautiful. So you can play the same game for the y component. The y component, okay, here is y instead of ex, and then here you have the y component of a vector product, so the mixture of z and x. But again, if you look, E0 is still E0, and EY is F20 here. Plus what? Well, UZ is minus U3. But F23 is minus BX. So minus BX times minus U3 minus plus. And here it is. And finally, minus UX, this guy, which is plus U1. And here, F21 is plus BZ So indeed, you have minus, as indeed this minus has to be. So I let you check it out. Also, check out also the third one. So you see that indeed, looking at the three, we've come up with indeed, we proved, okay, this one here, concern when mu is 1, 2, 3. Now let's have a look when mu is 0. What we obtained is that this is something that we already proved. So let's see if indeed can be expressed, is included in the same covariant equations that we saw. So this means, of course, the scalar product means what you see here. So the sum of the corresponding products of the components. But now it's a matter of playing the same game. So in particular, EX, so UX is minus U1. So here you should have a minus 1. But F01 is minus EX. So minus minus plus. You see that here you have F01, F02, F03. So you are moving along this row. So all the three components of the electric field with minus sign. But at the same time, you have all the three spatial components of view. All of them have the minus sign. So all plus. 0, 0, 1, 0, 0, 2, 2, 0, 3, 3. That's exactly what you have when you do this. So indeed, this is the generalization of Lorentz equation in a covariant way. Lorentz plus energy. It's not just about the momentum. It's both the momentum, the linear momentum of a charged particle, and its energy change under the influence of a given electromagnetic field, which is encoded in the electromagnetic tensor. So very beautiful, extremely beautiful. And you also see in this way that also from a dimensional point of view is beautiful to see, because you see U is adimensional. F is just electric and magnetic fields, but we know that in the Gaussian system they are homogeneous. So electromagnetic field times Q is a force. And indeed, the momentum over a proper time is a force. So also from a point of view, from a dimensional point of view, it makes sense. But of course, the most important message, the takeaway message here is we generalized how a particle moves and how its energy changes as a function of time under the influence of an electromagnetic field in a fully covariant way. Because it is a relation between a full vector and a full vector, which is the result of a contraction between a full tensor and a vector. Very powerful. And this concludes the part on the formulation of the covariant formulation of electromagnetism. This is the textbook I mostly follow. So Jackson, as I repeatedly said, but also Barone in Italian. And there are also other classical textbooks like the Brad. I took some pictures also from the Brad, as well as from Landau and Lifshitz. If you want to see things in a more geometric way, we carried out our calculations going through the components. But if you want to have a more geometric approach, is a little bit more, it's a higher level. So I would suggest, if you feel very confident, just you can move to this kind of Bible. This is very, very, this is also big. It's more than 1,000 pages. It was published 3 years ago. I advise you, if you want to, for more in-depth understanding of topics, the Thorne-Blanchard. Okay, so I'm left with, so today, okay, let me introduce in the final part of this class, what we are going to do, what we are going to explore more properly next time. I already shared this presentation. So this is about, we change a little bit subject, and this concerns about polarization of radiation. So what is that, how it works, and particularly how it is measured. I'm sure you are already familiar, but it's worth exploring because, for example, let me ask you, how many of you are familiar already Stokes parameters? None of you, as I suspected. So this is going to be very useful, as my guess was. So my guess was right. So okay, what is polarization? Well, this is just about the direction along which the given field, which you can think of electromagnetic, the electric field, just to fix things in your mind, but of course the same then line of reasoning applies to the magnetic field. So the direction along which the magnetic field oscillates and the way it changes as a function of time when this is the case. So just to figure out things, let's consider here a plane wave which is propagating along the z-axis here. Here you see the z-axis. So you already know that the electric and magnetic field, here we focus on the electric field, is just lies on a plane which is perpendicular. So having said that z is the direction of propagation means that the electric field lies in the xy field, the plane, okay? So in general, if we call with epsilon1 the unity vector corresponding to x-axis and epsilon2, I could have said ij, but I wanted to adhere to the notation that we will see in a moment. And epsilon2, the unity vector along the y-axis, well, in general, the electric field will be a combination of both fields, of both components along both directions, with its own amplitude. You call Ex the amplitude along the x-axis and Ey the amplitude along the y-axis, and you see that, okay, this term is just the term due to the wave. It's just the wave equation. It's just the result of a wave equation. So the result, of course, is just along the z. K is the vector, is the wave vector, so it's directed along z. So of course, here you just have kz minus omega t, where omega is the pulsation. But the important point here is that the direction of the electric field is given by the amplitudes Ex and Ey, but also on the relative phase, which I call phi x and phi y. In general, if you consider just one single electromagnetic wave, of course, the phase is fixed. So these two values are fixed. But as a matter of fact, one monochromatic wave. So you fix the frequency, wave that you observe is the result of many different independent waves. They have been generated by different atoms, which work completely independently of one another. So the phase the relative phase phi x and phi y can change in a random way, in a completely independent way. If you think that what you see is the result of electromagnetic radiation produced by a lot of atoms, which might work independently of one another. So there's no reason why you are to be expected with a fixed phase. Here I use imaginary quantities, but the comment is always the same. In physics, we conveniently carry out calculations on imaginary quantities, but when you mean something real, just imagine to take the real part of it. So in this case, the electric field, if you want to measure the electric field, just consider the real part. And you see that there are cosine and sines just showing up, which is exactly what we mean. Yes, so in general, the two phases are independent. So what does this mean? It means that if you look at the direction of the electric field, when phi x and phi y change in an independent way, in predictable way, it means that the resulting electric field has a direction, has no preferred direction. Can be here. There's no systematic, there's no preferred direction. So we say there is no polarization. And when there is some preferred directions along which the electric field mostly oscillate, then we speak in terms of a partially polarized wave. And we will see now, our goal is to explore how the polarization depends on both amplitudes and relative phases. Why this matters? Well, it does matter. The possibility that a wave is or not polarized, and if it is, which directions is polarized, it does matter. Because, for example, if you consider a wire of an antenna, of course, if the wave that is crossing the antenna, the wire, is the polarization of this wave is parallel to the wire itself, of course, the electric field will make electrons oscillate. But if, and this is the above case, if you consider the opposite case, this is meant to show an electric field which is perpendicular to the wire. If you have a polarized wave in which the direction of polarization is perpendicular to the wire, well, there's no way electrons can move because the electric field is perpendicular to the wire. So in one case, you have charge which are responding to the electric field. In the other case, you have no response. So indeed, the polarization makes a difference, and when the wave is polarized, depending on the direction of polarization, you have a different result also in the interaction with matter. This is important because, as we will see in the following, even when we start with an unpolarized light, which is exactly, for example, the light that you get from observing the sun. For the very same reason I was telling you before, when you see something which is emitting light and there's no preferred direction, indeed the result is that all the possible magnetic field, there's no preferred direction. So you have oscillations which are equally probable for any directions. So when you time average, the time average is zero in terms of direction of polarization, not instead of the intensity, of course. So what this means? Well, it means that if you use, for example, glasses which are polarized, polarized glasses, means that they allow light only to get through only the light whose electric field is, for example, vertical, in the case of sunglasses. We will see that the reflected light from ground acquires a degree of polarization. So even if the incoming light is unpolarized, as the light of the sun, the reflected light is polarized. And in particular, the horizontal component of the electric field is much less suppressed than the vertical one, which is the reason why sunglasses for polarized light are very effective in screening, in suppressing the reflected light, because the reflected light is mostly polarized horizontally. So this is just an application of why this is very important, and why, for example, you can get an example of the way you can get polarized light from an originally unpolarized light beam. This course is astrophysical processes, so it's interesting to see in which astrophysical examples this can be the case. Very well-known and powerful sources of polarized light are neutron stars, which are here depicted as something which has a strong magnetic field, a large-scaled ordered magnetic field. Here you see a very beautiful dipole structure. We know that neutron stars can have much more complicated structures than this simple dipole, but in any case, some of them have really huge magnetic fields, 10 to 8, 10 to 11 Gauss, up to 10 to 15 Gauss. We measured them, and I'll show you how we did that. So you have a large-scale structured magnetic field, so the electromagnetic rotation, the electromagnetic radiation coming out can be easily polarized from the structure of the magnetic field and also the mechanisms of emission that we will see. So this is just an example. Here, this is pi, this capital pi is the degree of polarization. We will see what this is. So this is also a very important aspect, property of radiation, also in the astrophysical context, tells us a lot of information about the astrophysical source of the light. So studying the polarization is a powerful tool also to explore the properties of these objects. Let me introduce just this concept here. So a monochromatic wave, as I just copied what we saw before. You can see just as the electric field, which can be projected over a Cartesian plane, y and x, okay? So with the corresponding amplitude and phases. There are special cases depending on the relative amplitudes and phases. If you think, for example, that the two amplitudes along x and y are equal, and the phase difference is 90 degrees plus minus, you have circular polarization. What does this mean? Well, it means that the resulting electric field just describes the circle. And this is easy to think. Well, also if you think of the composition of harmonic oscillations onto different perpendicular axes, this is something that you should know from basic physics. So when you combine two harmonic motions along perpendicular direction with a different phase of 90 plus 90 degrees and have equal amplitude, the result is just uniform circular motion, which here in terms of the electric field means an electric field which describes a circle. So this by definition is circular polarization, because the electromagnetic field is just describing a circle. If the different in phase, so if they are in phase or 180 degrees difference, well, it means that they are zero at the same time and they are maximum at the same time. So the combination is just an electric field which moves along a given straight line. When the electric field is oscillating along a fixed direction, you have linear polarization. When you have none of these special cases, well, it means that the resulting electric field for a monochromatic wave, pay attention to that, for a monochromatic wave, you have an elliptical polarization. If you think of the most general combination of two harmonic oscillations with no special difference about phase and about, you have the most general composition is the ellipse. So elliptical polarization, because the electric field describes an ellipse. So this is just a graphical representation of this. And you see this ellipse is just the figure described by the resulting electric field. You can usefully define the so-called chi angle, which is the polarization angle, because it tells you how the ellipse is orientated with respect to your reference frame. So if you look, chi is the angle between the semi-major axis of the ellipse and the x-axis. It's called polarization angle. There's also another angle, which we call alpha, which is defined this way. The cosine, its sine, of course, are proportional to the corresponding amplitudes. Mind that these two angles are not necessarily the same, because if you consider the rectangle in which the ellipse is inscribed, of course, the two amplitude are the two semi-sides of this rectangle. So alpha in general is different, even if they look pretty similar, but they are different. Okay. So this is good to know that if you want, there is a relation between these two angles and the difference in phase, delta phi. This is just an exercise of geometry if you want to carry out. So once you know one of them, two of them, of course, you can derive the third. I'm not going to spend too much time on this. This is just So far, I showed you that you can project the electric field on a Cartesian plane with two directions, x and y. There is a completely independent projection, which is the base, instead of a Cartesian base, which is good for linear polarization, as we will see, there is also another base, which is the so-called circularly polarized base. But to describe this, it would take me a little bit longer than what I have. So I think I'll stop here. So next Monday, we will continue talking about polarization. Any questions?